Okay. Now, I just went to the chapter 13 handout, so please take a look. They should be posted on their files as IFAL 23. And let's get started with this chapter because it seems like he's gonna go pretty fast this time. So let me know when you all have access to the actual handout so we can follow it. Okay, so we all have access to it? Okay, that's good. Now, chapter 13 is gonna be all about conjugated systems. First of all, what does conjugated mean? Specifically, yes. Now, in this case, we're gonna have three different types of pi systems. We're gonna have conjugated, which is the best one, it's the most stable one, because we can do a lot of resonance in there, so that charges are gonna be really stable overall. So in this case, practically, you are gonna look for a continuous line that has sp2 carbons. So in this case, this little section, because we have double bonds, those 4 carbons are gonna be sp2, right? So that's gonna be the conjugated part. They have to be right next to each other. That's how you know that it's conjugated. Now, the second most stable system is gonna be the isolated system. Do we know how that one is gonna look like? Exactly. Just look at the name. They're gonna be completely isolated from each other. So they're gonna be something like molecule 3. So they're not gonna have that resonance stabilization as compared to molecule 1, which was really conjugated. So basically isolated means that the double bonds are really far away from each other. That's it. And then the very last one, the one that we hate because it's the least stable of all, it's cumulated. And that's gonna be whenever they're right next to each other. So for example, molecule 2, we have 2 double bonds that are next to each other. That's gonna be technically on, I forgot the specific name of it, but he's not gonna ask you. You just have to know the name of the actual systems. So it's just cumulated. So that's it. One question that you might get asked on this is gonna be to rank them in order of stability. So again, conjugated is more stable than isolated, and very last one is cumulated. So as long as you know that pattern, you should be good. Questions like these should be pretty simple. So for the next 3 molecules, which one is going to be the conjugated one? First one, second, or third one? Third one, this one is going to be your conjugated. So it's the most stable one. Which one is isolated? Exactly. And then the one in the middle is just cumulated. We have those double bonds right next to each other. So again, pretty simple concept. It's just looking at the structures and figuring out the pi system that you have. So questions on this? Again, pretty simple. Any questions? We're good? Okay, we're all good, it seems like it, but I see some people writing down some notes, so I'm gonna give you 1 more minute. And actually, those of you who finished writing down your notes, for the next 4 molecules, start to rank them in order of decrease in stability.
For number 1, is that 2 double bonds, or is that, would it be denoted by a speed to split it? You know what I'm saying?
Are we talking about that one?
Yeah.
That's just 1 double one.
Okay.
It's not 2. Yeah. It's just an odd shape. Okay. Which molecule do we think is gonna be the most stable? 1, 3, 4. Okay, so to find the most stable, what are we trying to find? The most conjugated overall. So I heard 1, 3, and 4 overall. No, the very first one is conjugated. You guys are correct. Third one, it's also conjugated. Very last one, it's also conjugated. So whenever you're comparing different conjugated systems, you're practically just counting the number of double bonds. The more double bonds you have, the more resonance you can do, so the more stable you are. So it's gonna be 4, exactly. This one is gonna be the most stable one. What's gonna be the second one?
Yeah, 1. It's decreasing.
3,
but
4,
most stable,
3,
right?
4.
Here's the thing, 3 has.
They have the same amount of bonds.
Yeah, but 3 has 3 double bonds close to each other, and then 1, which is technically not close to anything.
It's 3 because 4 has 4 conjugated, whereas 1 has 3 conjugated, 1.
We've established that 4 is the most.
4 is the most stable of all.
3 has 1 that's
3 is gonna be the second most stable. First of all, because we don't have a lot of ring strain in that molecule. We have to consider everything for stability. So we're forgetting about that.
So just to reiterate, what's the difference between 3 and 4 then, in terms of stability? Like,
4 has a lot of double bonds, plus it's basically just 2 benzene rings right next to each other. So resonance is gonna be constant in both of them.
so because it has 1 more double bond than 3. And
Yes,
they're both
basically.
conjugated, right?
Mm-hmm.
So let's say so for 4, right? Let's say the molecule has 4 double bonds or 5 double bonds, but the 5th double bond was isolated later in this. You know what I'm trying to?
Yes, so you would focus on the conjugated part the most.
So in that case, because it has an extra double bond, and it would still be more stable.
Yes, but if you want to draw the molecules, then I can explain it better. Question. What's the difference between 3 and 4 or 3 and 1? 3 and 1. So they both have the same amount of double bonds. The only difference is that we're not considered ring strain sometimes. So remember, you have to focus on every single aspect for stability of molecules. One of them is going to be steric hindrance. If we have rings, remember that ring strain. So a cyclohexene is going to be a lot more stable than that odd shape of a heart. So yes, cyclohard tank, yeah. And then molecule 2, what's that? What kind of system?
No, I still conjugated because it's still.
That's still conjugated.
But it's. Oh,
Look at this little path. All of those carbons in there are sp2. So because we have that continuous line of sp2 carbons, they're going to be conjugated, and this one is going to be the least stable one.
just because it has a list.
Mm-hmm. So again, it's pretty simple. As long as you know that ranking of conjugated, isolated, accumulated, you should be good. Yes.
3 and 1.
Mhm.
The more ring, less.
The more ring strain you have, the least stable you are. That's why molecule 1 is not going to be as stable as molecule 3, even though they have the same level of conjugation overall. Okay, question on the pi systems. Pretty simple, pretty easy questions, pretty easy points. So, okay, next aspect to talk about is actually something that you guys should remember from chapter 7, which is going to be configurations versus conformations of pi systems. Now, we only know the configuration system, which is basically cis and trans, right? They're just looking at the R groups connected to the double bond. If they're opposite to each other, that's the E configuration. If they're on the same side, C configuration. Now, we have a new one, which is going to be kind of close. You're actually close. Yes, exactly. So yes, super cis and super trans. Beautiful. That's going to be your conformation.
No, hold up. How did you come to the term that is super versus just regular?
There's a little S.
Yes.
But why?
Okay, let's talk about those guys. So super trans and super cis, or just S trans and S cis, more simple. Now, conformations, you have to keep in mind that they're only going to happen for conjugated systems. Okay.
Oh, because it's the double, 2 double, okay.
This time, instead of looking at the R groups themselves, we're going to be looking at the positions of the double bonds themselves. So that means that we're comparing everything to that single bond in between double bonds. So in that case, we have double bond pointing down, double bond pointing up, opposite sides. So it's going to be S trans or super trans. On the next one, again, we're looking at a single bond. We're looking at those double bonds. They're pointing on the same side, so it's super cis or S cis. Okay, so it's pretty simple. But any questions on this? Confirmation and configuration. Pretty good, pretty simple. We're still talking about the easy points on the exam. Okay, so for the next one, this one should be pretty simple. Yes.
Does it say molecule just because it can rotate on the?
Exactly. Perfect, beautiful. I wanted you guys to notice that. In the confirmation part, we have a single bonds. What do single bonds do all the time? They always rotate. So that means that we can alter the S trans to the S cis configuration. Okay, so keep that in mind. That's the difference between confirmation and configuration. Configuration stays the same regardless. You're not moving anything, you can rotate. Confirmation, you can rotate that single bond and achieve those two positions. And this one should be pretty self-explanatory. If we're talking about confirmation, which one is going to be more stable? Not there yet, but it's going to be the S strands. And then between those two molecules, which one is going to be more stable, left or right?
Same molecule. They're not. Oh, yeah, they are, but.
But what's the difference?
Well, the right one's is because there's less eclipse, there's less.
This single bond was being double bonds.
Okay, so remember, we always start by looking at that single bond. And we're going to look at the connections of the double bonds. Double bond is pointing down. Double bond is also pointing down from that line. So it's going to be the S cis conformation. So it's the least stable one. And then same process for the right molecule. We look at that single bond in between double bonds. This one points down. This one points up. Opposite, S trans. So this one is going to be the most stable one, or more stable than the other. So far, questions? Are we good? Very simple. It's basically just an expanded topic of like cis and trans, and that's it. Okay, now for the next one, let's look at 5 molecules. I'm gonna give you 3 minutes max to try and rank them. Did we find the full ranking? Think so. We got it. We got it. Okay. So what's going to be the most stable one? Why the first molecule? What do we see? Everything is trans, exactly. Now that you guys know the pi systems, configurations, confirmations, you're going to look at every single aspect always. So first step is identify the pi system. That guy is conjugated, so perfect, that's stable. Then for the conformation, this one it's S trans. And then if you look at each double bond individually, they're both trans. So this one is going to be the most stable for all of those reasons. Okay. What's going to be the second most stable?
5.
It's going to be 5. Beautiful. What kind of system is it? It is S strands, yes. And then each double bond, what's the configuration? This entrance. What's the pi system? It's conjugated. Okay, what's gonna be the third most stable? It's gonna be the second one. What kind of pi system do we see? Isolated. Do we have S trans S's? No. What about the actual configurations of the double bonds? The last one's trans and the first one cannot be determined. Okay, which one is the fourth one? What kind of system? Isolated. And then we just have cannot be determined. And this one should be trans. And then very last one is just going to be number 4. But what system is it? Isolated. Can we find the configuration? No. On 3. Oh, sorry. Yes, you guys are correct. Thank you for correcting me. So yeah. That one is C. So yeah. I'm relying on you guys to double check everything. Okay, so this one is isolated and these ones cannot be determined.
Why did we pick 2 again for the third one? So I get 1 and 5, so that's actually what I got. And then we said 2,
Yes.
all 3 of them are isolated. Is that because it's E trans?
So basically, after you identify your pi systems, we know the ranking. Then after that, you're gonna look at both configuration and conformation. So in this case, we know that we're not gonna be able to get conformation because it's not conjugated. The configuration, you have to look at each double bond individually. The more trans you are, the better it is.
Right.
So that's why molecule 2 is gonna be better because this one, it's E. The very first one.
Okay, I'm sorry. But what about the 2 compared to 4?
2 compared to 4. Okay, so 2 compared to 4, we have those 2 double bonds. They are not conjugated, so we don't have S's or S trans. Can we find cis and trans from each of those double bonds individually?
Oh, I see what you're saying.
Exactly.
Got it.
Exactly.
Okay.
Mono-substituted double bonds are not going to be able to get a configuration. Okay, so questions on this topic. Pretty simple. Basically, the more trans you are, the better it is. The more conjugated you are, the better it is. Okay, and then let's start talking about the next concept, which is going to be UV spec. I think he briefly talked about this. He was talking about sunscreen and chlorophyll, maybe? I don't remember exactly. Something about waves, yes. More specifically, why would we use UV spec? To determine energy? So yes, in this case specifically, remember, we're talking about the pi systems. So the more conjugated you are, the more visible you're gonna be basically under UV spec. So the important part is that we use it to determine conjugation and the pi bond systems that we have. And what it actually is basically just the absorption of radiation under that UV visible range. Again, those are just the concepts. You are probably not gonna get tested on the actual definition of that. The thing that you have to remember is the trend boxed in pink in here. Now, in this case, remember, conjugation, we love that system. It's the most stable one. Now, because it's the most stable one, it's not going to be as reactive. So that means that it's going to have low energy. Okay, keep that in mind. The more stable you are, the less energy you have. And then the more conjugation you have, the longer the wavelength that you're going to see in the UV spec. So again, that trend is very important. That's going to help you figure out a lot of the answers in here. And in this case, let's start with the very first one. He's asking for the longer wavelength. So automatically, what are we trying to look for?
Energy level?
What about energy level? Higher or lower? Lower energy level, exactly. And then we're also looking for the conjugated system. So between those 2 molecules, which one is conjugated? First one. So this one is going to have the longest wavelength. And then for practice, what's the second one? isolated. So far, questions on that? Pretty simple. We're all following, we're writing our notes, okay. Okay, and then for the next two molecules, this time they're pretty large. And this time the question is not asking about the wavelength, they're asking about the energy. Which of those molecules is gonna have a lower energy and why? First one,
I said the second, because
Second.
the double bonds are conjugated.
Oh, and there's more pi bonds.
exactly. This one has 3 double bonds as compared to the first one. The first one only has 2 double bonds. So which one can be stabilized more is going to be the second one. Okay. So for questions on that one. Same type of question, but he's asking something slightly different. Yes.
So these two right here, they're right next to each other, so they're conjugated, right? Let's say these double bonds were like spread out, they're all isolated. Would we
prefer the less pi bonded conjugated or the more pi bonded?
In that case, it would be isolated. We would just be talking about isolated systems, right?
Yeah, but there's more pi bonds is what we're talking about. So what takes pi bond number of pi bonds or the conjugation versus isolation aspect?
Do you understand the question?
No, because you two like overlapped each other, so the question got mumbled.
Okay, so we have two, and they're both conjugated, right?
Mm.
As opposed to we have 3 over here, but let's say those 3 double bonds were spread out in an isolated fashion. So
Mhm.
all 3 of these double bonds are isolated.
Mhm.
Which one would be more stable? The 2 which are conjugated or the 3 which are isolated?
If we're talking stability, then we're using the same process as we did before. We would be looking at configuration and conformation of each of those. More specifically, we would just look at the configuration of each of those.
So
So-
then it would be the most
So if
conjugated.
it was three cis isolated versus 2 trans conjugated, what would be preferred?
Conjugated.
Conjugated?
Conjugated is always the most stable one. Okay, between those two molecules, if we're asking for the shorter wavelength, why the one on the left? What kind of system?
Higher energy, therefore.
What about the next one? What kind of system is that? Conjugated, exactly. In this case, it's a little bit odd to see it because we have that carbonyl area, but still, it's gonna be considered conjugated.
It's like the opposite.
The opposite of
So
stability.
No, short wavelength meaning it's higher than.
Yes.
Okay.
Okay, and then between those two, which one is more stable? Should be pretty simple. So yeah, this one is gonna be, whoops. As trans and both double bonds are E. So this one is the most stable one. The other one is also as trans, but they are both in the cis configuration. So again, same process. The more trans you are, the better it is. So far, questions on that? We're good? Okay, now. Next topic. This is going to be actually a little bit harder to explain, and that's where your question comes into play actually with the orbitals. So that's when he finished the actual, actually, I think the lecture, he finished with this. Yeah. Okay, so actually, before we do anything, what's molecular orbital theory? When do we use?
Explain why the electron and corresponds to that particular orbital.
Okay. When do we use it?
Comparing to differently oriented elements like sp3 carbon versus sp carbon.
Kinda in a way, but not really. Okay, so this theory is only going to come into play whenever we're talking about conjugated systems. Okay, and something to keep in mind is that carbocations, anions, and radicals, they're all gonna be considered sp2 for this class. So let's start talking about this. Let's start with the easy one, which is gonna be butadiene. Now, first of all, we're just gonna start by looking at the molecule. And first of all, how many sp2 carbons do we see? Which is, give me a number. 4. 4 sp2 carbons. Now, depending on the number of sp2 carbons you have, that's gonna correlate to the number of orbitals that you have. So that's why in the diagrams you have 4 lines. That's representing that. Now, technically, we can start drawing out each orbital in here. Now, in this case, because we have double bonds, each of those carbons is going to be contributing 1 pi electron. So in total, we have 1, 2, 3, and 4 pi electrons. Okay, so far, are we following this? Are you good? Okay, now, after that, now you can start filling out your energy diagram. Now, there's going to be 2 different types. There's going to be the ground state and the excited state. You're always going to start by looking at the ground state. That's what is going to determine everything. Now, you're always going to start from the lowest in energy, and you're going to start filling it up until you go to the top. Now, in this case, we have 4 electrons. So we have 1, 2 electrons, and then 3 and 4. Okay. We always start from the bottom to the top. So far, questions on that? We're good? Okay, now let's start to get into some definitions. We're gonna have, first of all, how do I explain this? Okay, so we have 4 orbitals, right? That's an even number. Now, whenever you have an even number of orbitals, you're only gonna have 2 types of orbitals. We have the bonding orbital, the ones that are actually filled, and we have the anti-bonding orbital, which sometimes we just represent with a little star at the beginning, okay? So again, they have to be the same amount of orbitals between each other. So if you have 2 anti-bonding, you need 2 bonding, okay? So far, pretty simple. Okay, now, next ones, you guys are gonna be asked for the HOMO and the LUMO orbital. What's the HOMO orbital? Did he ever explain it? We just learned this today. LUMO, yeah, it's really with Harry Potter, but in this case, it's not really. But either way, let's start with HOMO. That's going to be the highest occupied molecular orbital. And that's actually in the 2nd page from this, actually, the actual definition. Now, to find the HOMO orbital, you're finding, first of all, the orbital that has at least 1 electron, and you're looking for the highest n energy. So basically, pi 2 in this case instead of pi 1. Pi 2 has higher energy than pi 1, and it has 2 electrons. So that's how we know it's HOMO. Now, next thing that you have to know is that HOMO and LUMO are always going to be right next to each other. So if HOMO is number 2, LUMO is going to be 3. Now, the definition for LUMO is going to be that you're looking for the lowest orbital in energy that has no electrons at all. So far, pretty simple. Questions so far? We're going to be doing a lot of practice ones on this. So if we're not getting on the first try, we're going to get it probably on the last one. So it's always going to be the next one. Yes, they're right next to each other.
It's always 2 and 3.
It's not always 2 and 3. Don't memorize that. It's not always 2 and 3. They're always next to each other. Yes. Okay, now we have the ground state. So now let's talk about what's going to happen for the excited state. First of all, you have to keep in mind that HOMO and LUMO are going to stay the same in the ground and excited state. Now, the only difference that's going to happen is that basically we're just going to put some UV light into the ground state, and that's going to be exciting one of those HOMO electrons. So what's going to happen? One HOMO electron is going to jump up to the LUMO orbital. So in this case, pi 1 is going to remain the same. We're not touching it. We're only dealing with the HOMO orbital. So only one of those electrons is jumping up to get the excited state. It doesn't matter. Yeah, he's not going to be asking about spins. Now, keep in mind, now LUMO has 1 electron, but it's still going to be considered LUMO. Why? Because we found those definitions from the ground state. Okay, so that's why I always recommend the students to start by looking at the ground state. Don't just jump straight into the excited state. Okay, so far questions, yes.
The, like, LUMO to LUMO, that electron doesn't change spin to be like. 'Cause what isn't there, like-
Technically, it can change, but I don't remember exactly what was his reasoning. He might explain in a lecture on Wednesday, but you're not gonna get asked for the spins. Yes, no. He's not gonna be asking for the actual like energy diagrams. This is just to help you because some of the questions is gonna be that, for example, for molecule 1,3-butadiene, how many pi electrons do you see in the HOMO orbital in the excited state? It's just 1, exactly. So that's it. Energy diagrams are just to help you. And then I did a little table at the bottom so we can fill it out. And technically, yes, you can just memorize those numbers. But again, it's gonna be easier to just learn how to do the energy diagrams than just plain memorization on the numbers. Okay, so in this case, I'm just gonna fill it up for you guys. Sorry? Oh, you guys are talking to each other. We have 2. We don't have any bonding. Sorry, non-bonding. Yes. 0, 1. And then we have 2, 1. 0, 1. And again, all of that information is just coming from the energy diagram. Yes. He's going to give you the name of whatever molecule he wants you to look at, and he's going to be asking specifically for any of the numbers in the table. So he could be for the excited state. How many electrons do you have in the bonding orbitals? So in that case, it would be 3. He's just asking for electrons in the bonding orbital. He's not specifying pi 1 or pi 2 or HOMO. Okay. So again, that table is very important. That's basically telling you the different questions that he could ask you. And now, we just have 1 minute, so I'm gonna leave this for Wednesday. And we're gonna do basically just 3 more examples on this theory, and that's it. And again, I'll be posting the correction for the answer key for chapter 11 and 12, so there should be no questions on that. Plus, I'm gonna send an email explaining everything, so hopefully that helps. And I'll see you guys Wednesday. We're gonna continue with the chapter 13 handout.